Good evening, everyone. So today we'll start the 15th lecture of stochastic processes. In the last class, we saw everything about TTMC. This class we'll look at CTMC. This is continuous time Markov-Chain. So in DTMC we had a stochastic processes XL and greater than or equal to 0. So which where the state space S was discrete and also has the Markov property. The DTMC, we had the evolution of state in discrete time. So the time space. So in a sense, what we had was we had a model of evolution of the state. So we had xn plus 1 as a function of xn and some other random variable un, random sequence un, which are IIDs. So we had evolution of the state of the system without any notion of how much time it spent in the state. We know that the transitions from one state to other state would occur at discrete time points. So that's why this was discrete time Markov chains. In this app, now we'll start studying continuous time Markov chains. So CTMCs, they also have the Markov property. And since they are chains, they'll also take values from there. So they'll also have the Markov property. Uh, they'll also take discrete values in the state space because you're still working with chains, but they evolve in continuous time. Okay. So for CTMCs, we'll show that the time spent in a state will be seen as an exponential distribution that we'll see today, which is a property for Markov. And we also remember that Poisson process also had interval times as exponential. So Poisson would be a special case of CTMC. So now we'll go back to the. We'll first define mathematically what CTMC is. So a process. A discrete set of states. So the at any time, the state could be a discrete state of set of sets. It satisfies the Markov property for all t comma s greater than 0 and any state j belongs to s such that so probability of your state at t plus s is equal to j conditioned on is just probability of. So here this is the entire history. You know at what states at what time the states were for all u which is less than s. Xt plus s equal to j conditioned on xs. Okay, so what does it say? You just need to know. So here you will have at all points. So you'll have x0, x0.0001, x0.0002, like any number you give, not discrete time. You'll have the continuous, at each point, the whole history. This is the whole history. You'll have the whole history. So the Markov property states that even if you have the condition on the whole history, the probability is same as just knowing the latest update. The latest update would be at XS. So if process follows this property, then it is known as a continuous time Markov chain. The idea behind the continuous time Markov property of continuous time Markov chain is the same as DTMC. The idea is that given the past and the present, the future is independent of the past. It is only dependent on the present. That is condition. The condition is that you are given the past and present. Unconditionally, however, the future and the past are not independent. Yeah. So now let us take an example. Let us see the Poisson process. Go back and look at the Poisson process. So here we had the counting process, NT. This counting process is of rate lambda. And we also know that NT takes values in natural numbers. So now I want to find the probability of NT plus S is equal to J conditioned on NU, U less than or equal to S, and NS equal to I. We know that at NS it is I. So this I can write it as probability of NT plus S is equal to J, sorry, NT plus S minus NS equal to J minus I. I know because NS equal to I can condition it on this. Condition on NU, U less than or equal to S, and NS equal to I. Now, this NT plus S minus NS is basically an increment. And we know from the Poisson process that they have independent increment property. So they'll not depend on the previous values because previously all the increments are till just NS. NT plus N and NS, there are no overlapping between NS and N0 to NS and NT plus N, S minus NS. So this will be independent. So as you can write probability of NT plus S minus NS equal to J minus N. Right. Now going from here to here, we have used the independent increment property of Poisson process. Right. This again we can write back as P of NT plus S equal to J conditioned on NS equal to I. So yeah, this shows that the Poisson process NT, Poisson process NT is a CTMC. Okay, so in DTMC, we saw that we first assume time homogeneity that the it does not depend on the probability transition matrix does not depend on time, and we also had to define a DTMC. We had the state space and the transition probability matrices. Uh, so here also we will define the transition probability function for CTMCs. So we are given transition probability matrix, CTMC, the stochastic process, which follows the definition that we just defined CTMC. Now we're using the property of time homogeneity. So this stochastic process has the property of time homogeneity. So what does it mean is, so probability of xt plus s equal to j, conditional on xs equal to I, does not depend on the state on the time s. So this does not depend on time s, and it's just a function on how much you have incremented. So this is Pij. So this is basically equal to probability xt equal to j, condition of x0 equal to y. It is the transition, the condition probability or the transition probability depends on what is the increment of time you're looking at, but not at the state, not at the time uh, with which you started. So we'll use this homogeneity property. So since there we had a transition probability matrix, so we will have the same transition probability matrix here also. So transition probability matrix will denote it with PT, and it will have the elements P1 1 T, P1 2 T, P2 1 T, P2 1. If it is a two-state function, it will be just Pijt, a matrix with elements having Pijt, and Ij belongs to the state space, and Ij belong to the state space. So what we can think of this as a family of matrices indexed by t greater than 0, right? So what happens is you give me a t every time, you get a probability transition matrix. So similar to the TTMC, we observe some remarks here. So first remark is P of t is stochastic matrix. Right. So for all I comma j t greater than 0, Pij t is greater than or equal to 0. And for all I in the state space, summation of j for all state space Pij t equal to 1. So what does this mean is the row sums equal to 1, similar to what we had in TTMC. And also we'll define something which is trivial, but Pij0 is 0. So what does this mean is that if I not equal to j and Pjj 0 equal to 1. So if you're not looking at any time increment, then basically you can't jump instantaneously from one state to you jump instantaneously from one state to another, but you need some interval to jump from one state to another. And if you are looking at no interval, then there is no jump. So the probability that you'll stay in the same state is 1. This is there. So using these two, what we can say is The transition probability matrix P of 0 is an identity matrix because it will be of the form 1 0 0 1. So the second remark is the Chapman-Kolmogorov equations that we derived for DTMC will still remain same, and it will just be now instead of the discrete time, you'll have continuous time. So the probability transition matrix at T plus S will be probability transition matrix and probability into probability transition matrix at S. The proof for this would be the same that we have done for DTMC. There is not much change in it. So one more note here is that unlike the DTMCs, there is no one-step transition probability matrix that determines PT for all other T. The so there are some more results which hold for DTMC and CTMC, and the proofs for which are same. So I'll note those down. So suppose you have a stochastic process, which is CTMC, then the following hold. So what are the following is for all 0 less than T1 less than so on less than Tn, and all I0, I1, so on, In belong to a state space. Probability that x of T1 equal to I1, comma x of T2 equal to I2, so on, x of Tn equal to In, conditioned on x of 0 equal to I0. This is something we looked at while deriving DTMC. That will remain same. It will be just transitioning from I0 to I1 with the interval T1 because 0, you're starting from time 0 into you're transitioning from I1 to I2. But now the interval you're looking at is going from T1 to T2. So it will be T2 minus T1 into I2 to I3. And now the interval that you're looking for is T3 minus T2 and PIN minus 1 IN Tn minus Tn minus 1. So this is something we saw in DTMC also, how to calculate the finite dimensional distributions, conditional finite dimensional distributions. Now you can, since you have the conditional finite dimensional distribution, you can also calculate the finite dimensional distribution for a CTMC. So for the same assumption, P probability of x0 equal to I equal to pi I. So if we have this, so this is the stationary vector, probability vector, which this is the starting distribution of the starting state. If you know this, then the xt1 equal to I1, xt2 equal to I2, and so on, xtn equal to In. This becomes summation I0 belongs to state by I0, Pi0 I1, T1, Pi1 I2, T2 minus T1, so on, Pin minus 1, In, Tn minus Tn minus 1. This is also something we saw in the last time. So in order to specify the finite dimensional distribution of CTMC, in general, we need the initial distribution. So this is the initial distribution. And the transition probability PT. So you need the transition probability PT and initial distribution. Okay. the contrast with DTMC stochastic process. Um, in for DTMC, it is the complete stochastic process completely specified by the initial distribution and one-step transition probability matrix. Here, you need the initial distribution and the transition probability function, the P of T. Uh, so next we'll see, since it is a continuous state and there are finite number of states that the Markov state space can take. So basically what happens is you can uh, there'll be there'll be transition times of jumping from one state to another. So you need to know um, how much time does uh, the Markov chain in continuous time spend in one state. So that time we call it as sojourn time. Right. So let us view a CTMC xt t greater than equal to 0, randomly going from state to state and spending some random amount of time in each state. Right. So you have a CTMC. Now what I do is I'll define y of t. This is infimum s greater than or equal to 0 such that xt plus s is not equal to xt. So yt is the remaining time that the process spends in the state that is in at time t. So what this means that so suppose you at time t you have observed that it spends that it is at state I, right? Now yt, what it says is, suppose at here some uh, yeah, some random time, here it jumps to state j, right? Then what is the time it has spent in state I? This time is known as yt. So the remaining time, it need not be that it started at state I at t. It could have jumped to state I at some time previously, some delta. It could have stayed till t, but the latest observation you know is of t at t. And then yt gives the remaining time the process spends in that state. That is a time t. So now the theorem is for all I belongs to S, t greater than or equal to 0, and u greater than or equal to 0. Probability of yt greater than u conditioned on xt equal to y is e power minus ai. This is of exponential form. The conditional probabilities of exponential form, where ai is a positive real number, right? Which also includes the infinity. So this what does the real state is that given the state at time t, the remaining time that mm, it stays in the Markov process stays in state I is exponentially distributed with a parameter that depends on the state that it is currently. So intuitively, what we can see is that this result is necessary for Markov property to work. The necessity that it is exponentially distributed, and also that the parameter depends on only I but not on j. If it also depended on j, then you needed to know what the previous previous to previous state was, then the Markov property would fail. So the remaining time that it stays in the current state should only not only depend on how much time has already been spent, it should depend only on the current state, and also it should not depend on how much time it has already been spent in the state. Because if you want to know how much time it has been spent in the state, you need to know what the previous state was and when did it shift the previous state, so that you don't want to depend on the past, you just want the present. So for Markov property to hold, the two things that need to be checked is the remaining time should depend only on the current state and not on how much time that has been spent. So from these two, we can see that the memorylessness property, we observe an exponential distribution. Something similar we observed in DTMC, where it was a geometric distribution. So yeah, we'll do a proof for this. We'll define GIU as probability of yt greater than u conditioned on x equal to y. This is something we have just defined. So we can write GI u plus v as probability xs equal to I, t less than or equal to s, less than or equal to t plus u plus v, condition on x equal to y. This is basically probability of xs equal to I, t less than or equal to s, less than or equal to t plus u. So I'm breaking up the interval, and xs is equal to I, t plus u less than s, less than or equal to t plus u plus v, condition on x equal to y. And now I can use condition on x equal to y into probability of x is equal to I as belong to t plus u plus v, condition on x equal to y, x is equal to y as belongs to comma t plus u. So this first part is GIU, and the next part is probability of x is equal to y as belongs to t plus u, t plus u plus v. From Markovity, this depends on only on x t plus u equal to I. And then we have GIU, GIV. So basically from this we can see that GIU is of the form e power minus AIU, right? For some 0 less than or equal to A less than or equal to infinity, or GIU equal to 0 for all u greater than 0. So this AIU can be written with respect to, so you can take infinity, AI is infinity, and then GIU would be 0 for all u greater than 0. So from this, uh, we can see that CTMC states can be classified as three things. One is an absorbing state. Second is a stable state. Third is an instantaneous state. So absorbing state is if AI equal to 0. So if AI equal to 0, this GIU implies GIU would be 1 for all u. So for any amount of time you take, the probability that yt would be greater than any number condition that at time t or at state I would be 1. So will always be at state time. So hence data is absorbing state. If AI is between 0 and infinity, but not 0 and infinity. So basically you have some number, some positive number for which mm, you will stay with some positive number between 0 and 1, which you will stay in the state. So hence it is stable, but it will transfer to other state, like there'll be a jump to other state. And instantaneous if AI equal to infinity, right? So what happens if AI equal to infinity, then GIU equal to 0 for all state. So technically what it means that the moment you go to that state, you instantly come out. So you can say that mm, uh, that state doesn't matter because you just jump and go and come back at the same time. So for simplifying that assumption, what we'll do is we'll not deal with instantaneous states. We'll focus on pure jump CTMCs that evolve by moving randomly from state to state and with probability one spending positive amount of time in each of the states. So any Markov chain which doesn't have an instantaneous state is known as a pure jump Markov chain. Okay, so yeah, that is it for today's class. In next class is probably be the last class, and we'll just see pure jump CTMC and a regular CTMC, two types of CTMCs, and we'll see communicating classes, recurrence, the same things which we saw in DTMC. We'll just go through them, and I think yeah, that will be it. We'll see some examples of birth rate processor and all, and how to calculate, similar to what we saw last time for the DTMC. Thank you. I'll stop.